Right now, while you are lying in this bed, there is an object made of human hands that is more than 24 billion kilometers away from the sun. It has been traveling for over 46 years without stopping. It crossed the boundary of the solar system and entered interstellar space, a region of the galaxy that no human-made object had ever reached before. Tonight, you are going with it, not to where it is right now, to the beginning, to a launch pad in Florida in the summer of 1977, and then outward, slowly, across every kilometer of that distance, through every year of that journey, until you arrive at the place where the sun's influence ends and the galaxy begins. Welcome to Quiet Science at Bedtime, a storytelling channel where every journey is built entirely on real research and current scientific understanding. This channel is still very new, and if tonight's story brings you something, we would genuinely appreciate a subscription, a like, and a notification turned on. It helps more than you might think. Everything you are about to hear is based on real scientific fact. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. You are standing on a launch pad at Cape Canaveral Air Force Station, Florida. The date is September 5th, 1977. The time is 12:46 in the afternoon, Eastern Daylight Time. The air is warm and thick with humidity, the way late summer Florida air always is, carrying the salt smell of the Atlantic 2 kilometers to the east. In front of you, standing 49 meters tall on Launch Complex 41, is a Titan IIe rocket with a Centaur upper stage. It weighs approximately 632,000 kilograms, fully fueled. At the tip of the payload fairing, nested inside a protective aeroshell, is a spacecraft that weighs 721.9 kilograms. Its name is Voyager 1. The mass budget for the entire spacecraft was calculated and recalculated to the gram. Every kilogram launched into deep space costs energy, energy stored in the chemical propellants loaded into the rocket stages below. The engineers at the Jet Propulsion Laboratory in Pasadena, California, knew this. Every component of Voyager 1 was chosen, tested, and placed with that constraint in mind. The launch window for this mission was determined not by politics or schedule, but by orbital mechanics, specifically by a rare alignment of the outer planets that occurs approximately once every 176 years. In the late 1960s, a graduate student at Caltech named Gary Flandreau calculated that in 1977, Jupiter, Saturn, Uranus, and Neptune would be positioned in a configuration that would allow a single spacecraft, using gravitational assists at each planet, to visit all 4 in sequence without carrying the fuel that would otherwise be required. The trajectory had a name: the Grand Tour. In this window, the specific arrangement of 4 giant planets across 400 million kilometers of space would not occur again until approximately 253. The countdown reaches 0. The Titan IIe's twin solid rocket boosters ignite first, producing a combined thrust of approximately 13.3 million newtons. The acoustic energy from the ignition is so intense that water is pumped onto the launch pad at a rate of 300,000 liters per minute, specifically to absorb the sound waves, which would otherwise reflect back up from the concrete and damage the spacecraft. The water vaporizes immediately on contact with the exhaust plume, producing the vast cloud of white steam that billows outward from the base of the launch structure. The clamps release. Voyager 1 rises. At this moment, everything Voyager 1 will ever do, every measurement it will ever return, every discovery it will carry back across billions of kilometers, all of it begins here, in this column of fire and steam, In this 90-second Florida afternoon, you watch it rise until it becomes a point of light, and then it is gone. The sky over Cape Canaveral returns to ordinary blue. Let's talk about what is inside the spacecraft, now climbing through the upper atmosphere and preparing to ignite the Centaur upper stage for its departure from Earth orbit. Voyager 1 carries 11 scientific instruments designed and built by different institutions across the United States. Among them, a pair of Vidicon television cameras capable of producing images at a resolution sufficient to resolve surface features on planetary moons, a plasma spectrometer to measure the density, velocity, and temperature of charged particles in the solar wind, a cosmic ray detector to measure the flux of high-energy particles from outside the solar system, a low-energy charged particle instrument, a planetary radio astronomy experiment capable of detecting radio emissions from planetary magnetospheres, a photopolarimeter to measure the intensity and polarization of reflected sunlight from planetary surfaces, a magnetometer on a 12-meter boom extended from the spacecraft body, designed to measure magnetic field vectors in 3 dimensions, an ultraviolet spectrometer, an infrared spectrometer and radiometer, and on the outside of the spacecraft bus, mounted at the end of a boom to distance it from any electrical interference produced by the spacecraft itself, a triaxial fluxgate magnetometer, and beyond it, a second magnetometer of a different type, 2 separate instruments measuring the same thing so that if one fails, the mission continues. The people who built Voyager 1 were thinking about failure in every direction. They were also thinking about something else, something that had nothing to do with planetary science. Bolted to the body of the spacecraft is a 12-inch gold-plated copper disc. Its dimensions are 30.48 centimeters in diameter and 1.0 millimeter thick. It is mounted in an aluminum protective cover, and on the cover itself is engraved a diagram showing how to play the record and where the spacecraft came from. The diagram uses the hyperfine transition of hydrogen, the most abundant element in the universe, with a well-defined and universally constant transition frequency of 1.42 gigahertz as a universal unit of measurement. Any civilization with sufficient technology to intercept the spacecraft and read the cover would have access to that same constant. They could decode the diagram. They could play the record. The record contains 115 images encoded in analog format, depicting Earth, human anatomy, scientific diagrams, landscapes, cities, and scenes of human daily life. It contains 55 greetings in different languages, including ancient Sumerian and modern Mandarin. It contains sounds of earth, wind, rain, surf, thunder, the call of a humpback whale, the sounds of a chimpanzee, a human heartbeat, a mother's first words to a newborn child. It contains 90 minutes of music, Bach, Beethoven, Mozart, Chuck Berry's Johnny B. Good, a Navajo night chant, Georgian polyphonic folk music, a Peruvian wedding song, Japanese shakuhachi music, and others. The record was assembled under the direction of astronomer Carl Sagan, who chaired the committee that made the selection. Sagan later described the project as a message in a bottle cast into the cosmic ocean. Voyager 1 is that bottle. It is still traveling. The Centaur upper stage fires, and Voyager 1 achieves escape velocity from Earth's gravitational well. Escape velocity from Earth is approximately 11.2 kilometers per second, the speed required to leave Earth's gravity without additional propulsion. Voyager 1 exceeds this on departure. It is aimed not at a fixed target in space, but at a point in space where Jupiter will be when Voyager 1 arrives. A calculation that required knowing Jupiter's orbital velocity 13.1 kilometers per second, its current position relative to the Sun, and the precise trajectory of the spacecraft. The journey to Jupiter takes approximately 18 months. During those 18 months, the spacecraft crosses the asteroid belt, a region between Mars and Jupiter, populated by millions of rocky bodies, ranging from dust to objects hundreds of kilometers across. The asteroid belt is often depicted in diagrams as a dense field of tumbling rock, but this is a consequence of visual scaling. In reality, the asteroid belt is almost entirely empty space. The average distance between objects large enough to detect is on the order of 1 million kilometers. Voyager 1 crossed the asteroid belt without incident, as every spacecraft sent through it has, because the emptiness of space is so vast that collision is statistically improbable over distances this scale. Space is not crowded. Space is the opposite of crowded. This is difficult to hold on to intuitively. The human visual system evolved to perceive the scale of a forest, a plain, a coastline. It did not evolve to perceive the scale of a solar system. When you try to imagine the distance from Earth to Jupiter, approximately 600 million kilometers at the time of Voyager's approach, the number is available to you as a number, but not as a felt sense of distance. The felt sense simply does not exist for these scales. What exists is the mathematics, and the mathematics is exact. On March 5th, 1979, Voyager 1 makes its closest approach to Jupiter. The distance at closest approach is 348,890 kilometers above the cloud tops, measured, not estimated. At this distance, Jupiter fills a significant portion of the sky. You are closer to Jupiter than the Moon is to Earth. What Voyager 1 found at Jupiter reordered our understanding of the solar system. The cameras returned images of Jupiter's atmosphere at a resolution that ground-based telescopes could never achieve. The Great Red Spot, a storm system larger than the entire Earth, known to have existed since at least the 1600s, when astronomer Giovanni Cassini first described it, was resolved in detail for the first time. The storm is an anticyclone rotating counterclockwise, with wind speeds at its outer edges reaching approximately 432 kilometers per hour. It is not a surface feature. Jupiter has no surface. The Great Red Spot is a structure that exists in a gas giant with no solid boundary, sustained by dynamics that planetary scientists are still modeling. But the most unexpected discovery at Jupiter was not Jupiter itself. It was Io. Io is Jupiter's innermost large moon, orbiting at an average distance of 421,700 kilometers from Jupiter's center, completing one orbit every 1.77 Earth days. Its orbital dynamics are locked into a gravitational resonance with the next two moons, Europa and Ganymede. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance, called the Laplace resonance, after Pierre-Simon Laplace, who analyzed it in the 18th century, continuously deforms Io's orbit into a slight ellipse, which causes Jupiter's tidal force to flex Io's interior with every orbit. The tidal flexing generates heat, enormous amounts of heat that has nowhere to go except upward through Io's crust, emerging as volcanism. Voyager 1's cameras detected 9 active volcanoes on Io during the flyby. 9. Io's surface was covered in sulfur compounds in shades of yellow, orange, red, and white, painted fresh over geological timescales too short for impact craters to accumulate. Io is the most volcanically active body in the solar system, not Earth, not any known body anywhere. Io, a moon the size of Earth's moon, heated from the inside by the gravitational grip of a planet 317 times Earth's mass. No one had predicted this. The paper predicting Eo's volcanism on tidal heating grounds was published 3 days before Voyager 1's closest approach to Jupiter by a team that included Stanton Peele, Patrick Casson, and Ray Reynolds. The spacecraft returned confirmation before the ink was dry. You are passing through the Jovian system now. The cameras are clicking. The instruments are recording. The data is being stored on 8-track digital tape recorders on board the spacecraft and simultaneously transmitted back to Earth as radio signals at a frequency of 8.415 gigahertz in the X-band range at a power output of 22 watts from Voyager's transmitter. 22 watts, the power of a dim desk lamp, carrying humanity's first close-up images of the largest planet in the solar system across 600 million kilometers of space. The gravitational assist at Jupiter works exactly as Gary Flandreau calculated it would. Voyager 1's velocity relative to the Sun increases from approximately 10 kilometers per second before the Jupiter encounter to approximately 35.7 kilometers per second afterward. The spacecraft has not burned any additional fuel. The energy came from Jupiter, specifically from Jupiter's orbital momentum, which is enormous given Jupiter's mass of 1.898 times 10 to the 27th kilograms and its orbital velocity of 13.1 kilometers per second. Voyager 1 took a tiny, immeasurably tiny fraction of that momentum and converted it into additional velocity. Jupiter slowed down by an amount so small it is expressed in units smaller than the width of an atom per year. The interaction is real. The energy transfer is real. The mathematics that describes it has been confirmed in every gravitational assist maneuver conducted since for every spacecraft ever sent to the outer solar system. At 35.7 kilometers per second, Voyager 1 is now moving fast enough to escape the Sun's gravity entirely. This is the point at which its trajectory becomes genuinely open-ended. Given no further forces, no planets, no significant gas clouds, nothing to slow it down, Voyager 1 will travel in approximately this direction, at approximately this speed, for billions of years, long after the Sun has exhausted its hydrogen and expanded into a red giant, encompassing the orbit of Mercury and Venus and possibly Earth. Voyager 1 will still be moving at the same speed, in the same direction, in the same interstellar night. On November 12, 1980, Voyager 1 makes its closest approach to Saturn. Distance at closest approach, 124,200 kilometers above Saturn's cloud tops. This is the encounter for which the trajectory was specifically designed, and the reason the Grand Tour ends here for Voyager 1. The trajectory required to achieve a close flyby of Saturn's moon Titan, which mission scientists prioritized above all other Saturn system targets, placed Voyager 1 on a path that bent sharply out of the plane of the solar system. After the Saturn encounter, Voyager 1 is traveling upward relative to the orbital plane of the planets, northward in the conventional orientation of solar system diagrams, at approximately 35 degrees above the ecliptic plane. This trajectory cannot be corrected to visit Uranus or Neptune. The mission's grand tour ends at Saturn, but what it found at Saturn was worth the trade. Saturn's rings, which appear in Earth-based telescopes as 2 or 3 broad bands, were resolved by Voyager 1 into hundreds of individual ringlets. The ring system spans approximately 282,000 kilometers from the inner edge of the D ring to the outer edge of the A ring, but its average thickness is only about 10 to 20 meters, in places far less than that. An object with a diameter 282,000 times its thickness. If you scaled Saturn's rings to the thickness of a standard sheet of office paper, the sheet would extend for roughly the width of a city block. The rings are made almost entirely of water ice, with some rocky material in particles ranging from dust grain size to boulders several meters across. The individual particles orbit Saturn just as moons do, each at a speed determined by its distance from Saturn, all governed by the same gravitational dynamics that govern every orbit in the solar system. Titan, Saturn's largest moon and the primary target, did not disappoint. Voyager 1's instruments confirmed that Titan has a dense atmosphere, denser than Earth's at the surface, with a surface pressure of approximately 1.45 times Earth's atmospheric pressure at sea level. The atmosphere is composed primarily of nitrogen, approximately 95%, with the remainder being mostly methane and trace amounts of other organic compounds. Titan's surface temperature is approximately minus 179 degrees Celsius. At this temperature, methane exists in liquid form and cycles through an atmospheric process analogous to Earth's water cycle, evaporating, condensing into clouds, and falling as rain onto a surface where it collects in lakes and seas. Titan has lakes of liquid methane, rivers of liquid methane. It rains methane. Voyager 1 could not see the surface through the thick orange haze that would wait for the Cassini mission and the Huygens probe, which descended through Titan's atmosphere in January 2005 and transmitted 90 minutes of data from the surface. But Voyager 1 established that what was there was worth going back to see. After Saturn, the cameras turn off. There is nothing left to photograph. The outer solar system ahead of Voyager 1 is dark and empty. The instruments that can still function without a target continue recording. The magnetometer, the plasma spectrometer, the cosmic ray detector, the low-energy charged particle instrument, the plasma wave system. These instruments are now doing the long, slow work that will define Voyager 1's greatest scientific legacy. They are listening to the boundary. For decades, the spacecraft travels. The data returns. Year after year, the plasma spectrometer and the cosmic ray detector record the properties of the solar wind, the continuous stream of charged particles, primarily protons and electrons, that flows outward from the sun at approximately 400 to 800 kilometers per second, filling the heliosphere, the bubble of solar influence that surrounds the entire solar system. The heliosphere has a boundary. The sun's solar wind presses outward against the interstellar medium, the diffuse gas and dust that fills the space between stars in the Milky Way galaxy. At some distance from the sun, the solar wind slows down and stops. That boundary region is called the heliopause, and the space beyond it is interstellar space, the galactic medium that belongs to no single star. For years, the scientists at JPL watched the data and waited for signs that Voyager 1 was approaching this boundary. They had models. They had predictions. The predicted distance to the heliopause ranged widely in the literature, from roughly 80 to 160 astronomical units from the sun, an astronomical unit being the average Earth-Sun distance, approximately 149.6 million kilometers. Then, in 2004, at approximately 85 astronomical units from the sun, the plasma spectrometer detected a sudden and dramatic change. The solar wind slowed abruptly from supersonic to subsonic speed, from approximately 400 kilometers per second to nearly zero. This boundary, where the solar wind transitions from supersonic to subsonic as it rams against the interstellar medium, is called the termination shock. Voyager 1 had crossed it, but it had not yet reached interstellar space. Beyond the termination shock lies a turbulent region called the heliosheath, where the slowed solar wind piles up against the heliopause like water piling up in front of a slow drain. Voyager 1 spent 8 years crossing the heliosheath, its instruments measuring the increasingly tangled and turbulent magnetic fields in this compressed region. Then, in August 2012, At approximately 121 astronomical units from the Sun, approximately 18.1 billion kilometers, everything changed again. The plasma wave instrument detected a sudden dramatic increase in the density of ambient plasma. The density jumped by a factor of approximately 40, from about 0.0006 particles per cubic centimeter inside the helios sheath to approximately zero 0.08 particles per cubic centimeter outside. The magnetic field direction, which had been aligned roughly with the Sun's own magnetic field inside the heliosphere, shifted to align with the direction of the interstellar magnetic field. A cosmic ray instrument, which had been detecting increasing fluxes of galactic cosmic rays as Voyager 1 approached the boundary, recorded a sudden further increase. Voyager 1 had crossed the heliopause. It was in interstellar space. For the first time in human history, a human-made object was outside the solar system. The scientists at JPL confirmed this in September 2013 after careful analysis of the plasma density measurements. The announcement was made at a press conference. Don Gurnett, the principal investigator for Voyager's plasma wave experiment, played an audio conversion of the plasma oscillation data, the instrument's frequency converted to audible sound. The denser plasma in interstellar space produced a higher-pitched tone. The scientists in the room heard, for the first time, the sound of interstellar space. It was a tone, a pure, sustained tone, rising in pitch as the density increased, the sound of somewhere no human instrument had ever been. You are here now, in this place that Voyager 1 reached. The interstellar medium is not empty, but it is close. The particle density in the local interstellar medium is approximately 0.05 to 0.1 atoms per cubic centimeter, meaning that in a cube of space 1 centimeter on each side, you would find, on average, perhaps 1 atom, mostly hydrogen, some helium, traces of heavier elements. The temperature of this plasma is approximately 6,000 to 10,000 Kelvin, which sounds paradoxically hot, but temperature at this density means very little in terms of felt heat. Temperature is a measure of the average kinetic energy of particles. When there are almost no particles, the total thermal energy in any given volume is negligible, regardless of temperature. When there are almost no particles, the total thermal energy in any given volume is negligible, regardless of temperature. A cold defined not by temperature, but by the near total absence of matter through which temperature could be transferred to you. The nearest star to the Sun, Proxima Centauri, is approximately 4.24 light-years away. A light-year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. Proxima Centauri is therefore approximately 40.1 trillion kilometers from the Sun. Voyager 1's current speed, as of the time of this recording, is approximately 17 kilometers per second relative to the Sun. At this speed, if Voyager 1 were aimed at Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. The nearest star is 73,000 years away at the fastest speed any human object has ever traveled. Hold that for a moment, not as a number, as a duration. 73,000 years ago, anatomically modern humans were living in small groups across Africa and parts of Eurasia. The oldest known cave paintings had not yet been made. Agriculture was 50,000 years in the future. Every civilization that has ever existed, Sumerian, Egyptian, Greek, Roman, Chinese, all of them, every language, every poem, every war, every scientific discovery, every child ever born, all of that fits inside a fraction of the time it would take a spacecraft moving at 17 kilometers per second to reach the nearest star. That is the scale of interstellar space. Right now, as you lie in this bed, scientists at the Deep Space Network, a collection of large radio antenna facilities located at 3 sites spaced approximately 120 degrees of longitude apart around the Earth. Goldstone in the Mojave Desert in California, near Madrid in Spain, and near Canberra in Australia, are receiving signals from Voyager 1. The signals travel at the speed of light, 299,792,458 meters per second, at Voyager 1's current distance of more than 24 billion kilometers. A signal from Earth takes approximately 22 to 23 hours to reach the spacecraft. Voyager 1's reply, also traveling at the speed of light, takes another 22 to 23 hours to return. A round-trip communication with Voyager 1 takes approximately 45 to 46 hours. The transmitter on Voyager 1 produces a signal of 22 watts, the same power as when it launched. That signal, spreading outward in a cone from Voyager's high-gain antenna, a 3.66-meter dish, roughly the size of a large dining room table, arrives at Earth as a whisper, a signal power at Earth's surface of approximately 10 to the power of negative 16 watts. That is 1 watts. The Deep Space Network's largest antennas, the 70-meter dishes at each facility, are sensitive enough to detect it. To put the antenna's sensitivity in perspective, the total energy received from Voyager 1 over its entire mission to date, if converted to physical energy, would not be sufficient to light a standard incandescent bulb for 1,000th of a second. All of Voyager's data, all its images of Jupiter and Saturn, all its plasma measurements, all its magnetic field vectors, all its cosmic ray counts, all its records of the heliosheath and the crossing into interstellar space, has been received on that margin of energy, extracted from noise, reconstructed, verified, archived, and published for any human being on Earth to read. The signal is still coming. Voyager 1 is powered by 3 radioisotope thermoelectric generators called RTGs. Each RTG contains a core of plutonium-238 dioxide, a radioactive isotope of plutonium with a half-life of 87.7 years. Plutonium-238 decays by emitting alpha particles, releasing thermal energy in the process. The RTGs convert this heat directly into electrical power through thermocouples, junctions of dissimilar metals that generate a voltage when a temperature gradient is maintained across them. At launch in 1977, the 3 RTGs produced a combined electrical output of approximately 470 watts. Plutonium-238's half-life means that its activity, and therefore its heat output and electrical output, decreases over time. After 46 years, slightly more than half of one half-life, the RTGs now produce approximately 249 watts of electrical power. This degradation has been precisely measured and modeled. The mission team at JPL has had to regularly turn off instruments as available power decreases, carefully managing what remains of the spacecraft's electrical budget. The magnetometer is still operating. The plasma wave instrument is still operating. The cosmic ray detector is still operating. The low-energy charged particle instrument is still operating. The mission is estimated to continue returning scientific data until approximately 2025 to 2030, at which point the power output will have declined to the point where no instrument can be kept active. After that, Voyager 1 will continue traveling in silence, transmitting nothing, receiving nothing, carrying its instruments and its golden record into the dark. It will travel for billions of years. In approximately 40,000 years, it will pass within approximately 1.6 light-years of a star called Gliese 445, a red dwarf in the constellation Camelopardalis. Not a flyby in any meaningful sense, 1.6 light years is still an immense distance, but the nearest approach of any known star to Voyager 1's trajectory within any foreseeable time frame. After that, nothing. The galactic disk, the long emptiness between stars. Your breathing has slowed while you have been thinking about this. This is what the body does when it processes information that is too large to solve. When the mind encounters a scale, 73,000 years, 40 billion kilometers, the silence of an RTG slowly dimming across decades that cannot be resolved into action or worry. The nervous system releases its grip. The hypothalamic pituitary axis, which governs the stress response through the hormone cortisol, reduces its output when there is nothing to respond to. The amygdala, a pair of almond-shaped structures in the medial temporal lobes of the brain, each roughly 1.5 centimeters in length, reduces its alerting signal when the cognitive load shifts from threat detection to contemplation. Your body is doing this now. Cortisol levels in the bloodstream follow a well-documented circadian pattern. They peak in the early morning hours, approximately 30 to 45 minutes after waking, as part of the cortisol awakening response, which prepares the body for the demands of the day. They decline through the afternoon and reach their lowest levels of the day in the late evening hours, just before and during sleep onset. At this moment, in this position, in this hour, your cortisol is near its daily minimum. There is no threat, there is no task. There is a spacecraft traveling at 17 kilometers per second through interstellar space, and there is you, horizontal, breathing slowly, cortisol low, body temperature dropping at the rate required for sleep to begin. Both of these things are true at the same time. The transition into sleep is not a single event, it is a gradient. A slow dimming, stage 1 non-REM sleep begins when your brain's electrical activity shifts from the alpha waves of relaxed wakefulness, oscillating at 8 to 12 cycles per second, into the slower theta waves of light sleep, oscillating at 4 to 8 cycles per second. This transition is sometimes accompanied by a subjective sensation that researchers call hypnagogic imagery, brief, involuntary visual or auditory experiences that occur at the threshold between waking and sleeping. A flash of color, a heard voice saying a single word, a sudden sense of falling. These experiences are neurologically normal. They arise from the disorganized firing of cortical neurons as the thalamus begins its transition from relay mode to filtering mode, from transmitting sensory information to the cortex to blocking it. The images or sounds are fragments, not narratives. They dissolve before they can be completed. If you see or hear something at the edge of sleep right now, let it pass. It is your brain cycling down, not signaling something wrong. It is the sound of a system preparing for maintenance. Voyager 1 also has a fault protection system, an onboard computer that monitors the spacecraft's health and autonomously corrects anomalies if they fall within a defined range. Engineers call it the flight data system. If a sensor reads outside expected parameters, the system responds. It has been responding to anomalies quietly for 46 years, maintaining the spacecraft's orientation, keeping the high-gain antenna pointed at Earth, managing the power distribution between instruments. The spacecraft watches itself while the scientists sleep. Your brain does the same thing. As sleep deepens into stage 2 non-REM, the thalamus generates bursts of synchronized electrical activity known as sleep spindles. These are brief oscillations, approximately 12 to 15 cycles per second, lasting between half a second and 3 seconds, generated by the interaction between the thalamic reticular nucleus and the thalamocortical relay cells. Their function, confirmed across multiple lines of evidence in the sleep research literature, includes the active suppression of sensory processing during sleep. Sounds that would register in waking awareness are intercepted by the thalamus before they reach the cortex. External stimuli are attenuated. Stage 2 sleep also produces what are called K-complexes, large, sharp waveforms visible on electroencephalography recordings, characterized by an initial negative deflection followed by a positive component. K-complexes can be triggered by sudden external sounds, and they appear to represent the sleeping brain's active suppression of a response to that sound, the brain detecting the stimulus and choosing in the same neural event not to wake. The K-complex is the brain saying, "I heard that, and I am choosing to stay asleep." During this stage, the consolidation of declarative memory, the type of memory that stores facts and experiences as retrievable knowledge, begins its first pass. The hippocampus, a curved structure on the medial surface of each temporal lobe, approximately 5 centimeters long and shaped, as its Greek name suggests, like a seahorse, replays patterns of neural activity that occurred during the day. The neocortex receives these replays and begins integrating them with existing long-term memory structures. The science you encountered tonight, the RTG half-life, the plasma density jump at the heliopause, the sound of interstellar space played at a JPL press conference, is now being transferred from the hippocampus into the longer-term structures of the neocortex. By morning, some of it will be more accessible than it is right now. By next week, if you sleep adequately each night, more still. Sleep does not simply store memories. Sleep selects, compresses, and integrates them. What you know and how you know it is shaped, in part, by how you sleep. Now the delta waves are arriving. Stage 3 non-REM sleep, also called slow wave sleep, is the deepest sleep stage. The brain's electrical activity slows to below 4 cycles per second, sometimes to 1 cycle per second or slower. Large populations of cortical neurons fire in slow, synchronized waves that can be detected at the scalp surface as high-amplitude, low-frequency signals. The brain is more electrically coherent in this state than at any other time. During slow-wave sleep, your pituitary gland, a structure approximately the size of a pea suspended from the underside of the hypothalamus by a stalk called the infundibulum, releases pulses of growth hormone. In adults, growth hormone continues to regulate protein synthesis, cellular repair, and fat metabolism. Approximately 70% of daily growth hormone secretion occurs during the first slow-wave sleep episode of the night, timed to the onset of deep sleep by signals from the hypothalamus. Simultaneously, the glymphatic system activates, described first in the published scientific literature in 2012 by Macon Nadergaard and colleagues at the University of Rochester. The glymphatic system is a network of perivascular channels, spaces surrounding the brain's blood vessels, through which cerebrospinal fluid circulates during sleep. During slow-wave sleep, astrocytes, the support cells of the brain, contract by up to 60% of their waking volume. This shrinkage expands the interstitial space between cells, dramatically increasing the flow of cerebrospinal fluid through brain tissue. This flow flushes accumulated metabolic waste products, including beta amyloid, the protein whose aggregation is associated with Alzheimer's disease, into the venous drainage system and out of the brain. Your brain is washing itself right now. The waste products of a day's cognition are being cleared by a fluid circulation system that functions almost exclusively during sleep, that was completely unknown to science as recently as 12 years ago, that requires the physical shrinkage of your brain's supporting cells to operate. Sleep is not downtime. Sleep is the maintenance cycle. Let the slow waves deepen. Somewhere in interstellar space, at a distance that takes light more than 22 hours to cross, Voyager 1 is orienting itself. The spacecraft uses 3 pairs of gyroscopes to determine its orientation in 3-dimensional space, and thrusters that operate in pulses, each pulse lasting a few milliseconds, to maintain the pointing of its high-gain antenna toward Earth. Without this continuous automatic orientation maintenance, the antenna would drift off target and the signal would be lost. The navigation is done in absolute darkness. There is no reference frame except the stars. Voyager 1 carries a star tracker, which identifies the positions of bright guide stars, primarily Canopus, one of the brightest stars in the sky, located approximately 310 light-years from Earth in the constellation Carina, and uses the angle between these reference stars to determine its own orientation. Canopus is so far away, 310 light-years, approximately 2.93 quadrillion kilometers, that its position in the sky does not change measurably even as Voyager 1 moves billions of kilometers through interstellar space. It is close enough to be bright enough to use as a reference, and far enough away to be essentially fixed relative to Voyager 1's movements. The navigators at JPL chose it for exactly this reason. Decades before launch, the spacecraft knows where it is by looking at a star 310 light-years away, and from that, it knows where to point to find us. Your first REM-EM episode may be beginning now, or approaching. Rapid eye movement sleep, first described systematically in 1953 by Nathaniel Kleitman and his graduate student Eugene Eserinsky at the University of Chicago, is the sleep stage most associated with dreaming. During REM, the brain's electrical activity resembles the low-amplitude, high-frequency pattern of waking consciousness more closely than any other sleep stage. The brainstem structure called the pons generates rhythmic bursts of electrical activity that propagate upward through the thalamus to the visual cortex, creating the neural basis for visual imagery, even in the absence of visual input. These waves are called pontogeneculo-occipital waves, or PGO waves. Simultaneously during REM sleep, the brainstem suppresses voluntary muscle activity through the active hyperpolarization of spinal motor neurons. This condition, called REMatonia, prevents you from physically acting out the movements your dreaming brain generates. The muscles of your eyes are specifically exempt from this suppression, hence the rapid eye movements that define the stage. You may dream during REM of things you have encountered tonight, of a launch pad, of the amber glow of Jupiter's clouds, of the rings of Saturn resolved into hundreds of thin lines, of a tone, a single pure tone played from a speaker in a conference room, converted from the oscillation of plasma density in interstellar space. If you do, that is not imagination running unsupervised. That is the hippocampus and the prefrontal cortex working together across the architecture of the dreaming brain, integrating new information with existing structures, testing associations, consolidating understanding. You are processing what you learned tonight. Let it run. A typical night of sleep consists of 4 to 6 complete sleep cycles, each lasting approximately 90 minutes. The proportions within each cycle shift across the night. Early cycles contain more slow-wave sleep and less REM, while later cycles reverse this, with extended REM episodes and less deep sleep. The last REM episode of the night, in the hour or so before waking, may last up to 45 to 60 minutes. Your body will move through these cycles automatically. You do not need to manage them. The architecture of sleep has been refined over hundreds of millions of years of evolutionary history. The two-phase alternation of non-REM and REM is found in all placental mammals, in birds, and in modified forms in reptiles and fish. It predates the lineage that would eventually produce primates, hominids, and you. It has been in place running every night for longer than the continents have had their current positions. You do not need to direct it, you only need to be still. The cosmic ray detector on Voyager 1 is still functioning. It is measuring, right now, the flux of galactic cosmic rays, high energy particles, primarily protons, that originate from supernovae and other energetic events throughout the Milky Way and beyond, traveling through interstellar space at velocities approaching the speed of light. Inside the heliosphere, the solar wind's magnetic field partially deflects these cosmic rays, reducing their flux near Earth. Outside the heliosphere, in interstellar space, the full galactic cosmic ray flux is measurable for the first time by a human instrument. Voyager 1 is measuring the unfiltered radiation environment of the galactic disk. This data has been transmitted back to Earth and used to improve models of the heliosphere's shielding effect, models that matter for understanding how the galactic radiation environment affects the chemistry of interstellar clouds, the evolution of planetary atmospheres, and ultimately, the conditions that allowed life to develop on Earth. The galactic cosmic rays that Voyager 1 is measuring right now also pass through you. Some fraction of the ionizing radiation your DNA encounters over the course of your life originates from exactly the same galactic sources Voyager 1 is detecting in interstellar space. The connection is real, if diffuse. What the spacecraft is measuring out there is the same phenomenon that has been measured here, inside every living cell, for billions of years. The boundary is not as sharp as a map makes it look. Let the breath slow now. Each cycle of your lungs during sleep moves approximately 500 milliliters of air, the resting tidal volume. Your respiratory rate has dropped to perhaps 12 to 14 breaths per minute. The diaphragm contracts and relaxes, driven by the pre-Bötzinger complex, a small cluster of pacemaker neurons in the medulla oblongata, identified in 1991 by Jack Feldman and colleagues at UCLA, which generates the rhythmic respiratory drive automatically without conscious instruction. The heart maintains approximately 50 to 60 beats per minute in slow-wave sleep. Each beat propels approximately 70 milliliters of blood outward through the aorta. Over the course of 8 hours of sleep, the heart will beat approximately 24,000 times, moving approximately 1,700 liters of blood. Without a single conscious instruction, your body knows what it is doing. It has known for hundreds of millions of years. The stars that Voyager 1 will eventually approach, in 40,000 years, in 100,000 years, in millions of years, are already there. They are not waiting. They are not expecting anything. Gliese 445, the red dwarf that Voyager 1 will pass closest to in 40,000 years, is burning its hydrogen at a rate determined by its mass of approximately 4.26 solar masses, on a main sequence lifespan estimated at several hundred billion years. It will still be burning when Voyager 1 reaches its closest approach. Whether anything will be there to notice is a question that cannot be answered. But the record will be there, the golden disk, still mounted on the spacecraft body, still enclosed in its protective aluminum cover, still carrying its encoded images and its greetings in 55 languages and its 90 minutes of music. It will be there. The aluminum cover is expected to protect the disk from degradation on a timescale of billions of years in the interstellar environment, where the particle flux is low and there is no ultraviolet radiation from a nearby star to cause photodissociation. The instructions for playing it are on the cover. The key to the measurements is the hydrogen hyperfine transition. The diagram is engraved. Carl Sagan called it a message in a bottle. The bottle is still traveling. Let your awareness soften now. The delta waves are deep. The glymphatic flow is moving through your brain tissue, carrying the metabolic byproducts of today's thinking outward through the drainage channels. The growth hormone is in the bloodstream, signaling repair and synthesis throughout your body. Voyager 1 is traveling at approximately 17 kilometers per second, roughly 38,000 miles per hour, increasing its distance from the Sun by approximately 1.47 billion kilometers every year. By the time you wake in the morning, it will be approximately 720,000 kilometers farther from the Sun than it was when you lay down. In the time it takes you to sleep, the farthest human-made object in existence will travel the equivalent of almost twice the distance from Earth to the Moon, and it will still be going, and the signal will still be coming back. And somewhere in Goldstone or Madrid or Canberra, a 70-meter dish is pointed at a precise location in the sky, tracking a 22-watt radio signal crossing 24 billion kilometers of space, receiving it as 10 to the negative 16 watts of power, and turning it into data that human beings read, analyze, and share with other human beings. Because 46 years ago, a team of scientists and engineers in Pasadena decided it was worth doing, and then they did it. Let the sentence rhythm slow now. There is nothing more to solve tonight. The spacecraft is on its course. Your body is on its course. Both follow paths laid out before tonight. Both are doing what they were built to do. The cosmic microwave background radiation passes through the walls of this room. Through you, photons from 380,000 years after the Big Bang, stretched from near infrared to microwave by the expansion of space across 13.8 billion years, arriving from every direction simultaneously at a temperature of 2.725 Kelvin. The same photons pass through Voyager 1 in interstellar space, and through the 70-meter antenna in the California desert, and through the engineers at their consoles who do not feel them. No one feels them. They pass through everything. They are the universe's oldest light, and they are here in this room right now, and there is nothing you need to do about that. Let them pass. Let everything pass. The delta waves are yours now. The breath is slow. The body is repairing. The memories are consolidating. Voyager 1 is moving. If you are still awake, here is what tonight was. You stood on a launch pad in Florida in 1977 and watched the beginning. You traveled with a spacecraft through the asteroid belt and across 600 million kilometers to Jupiter. You saw 9 active volcanoes on Io. You saw Saturn's rings resolved into hundreds of ringlets. You crossed the termination shock and the heliosheath. You heard the tone of interstellar plasma. You learned the half-life of plutonium-238 and what it means for a spacecraft's power supply 46 years into its journey. You measured a signal of 22 watts across 24 billion kilometers. You learned that the nearest star is 73,000 years away at the fastest speed we have ever traveled. You learned that your brain cleans itself while you sleep, and that this has been happening every night for hundreds of millions of years. You learned that a golden disk, encoded with music and voices and images of human life, is traveling right now through interstellar space on a spacecraft that weighs less than a small car. All of this is real. All of it is still happening. Let us go back for a moment, not forward into the dark, but back to the spacecraft itself, to what it is made of. Because Voyager 1 is not simply a collection of instruments, it is a physical object, and understanding its physical construction tells you something about the people who built it and the era in which it was made. The spacecraft bus, the central body of Voyager 1, is a 10-sided aluminum frame, approximately 47 centimeters tall and 188 centimeters in diameter. It was manufactured at the Jet Propulsion Laboratory in Pasadena between 1972 and 1977. The interior contains most of the spacecraft's electronics: the computer command subsystem, the flight data subsystem, the attitude and articulation control subsystem, and the power distribution system. The total memory available to Voyager 1's onboard computers when it launched was approximately 69.63 kilobytes. That is not a typo, 69 kilobytes. A single low-resolution photograph on a modern smartphone contains thousands of times more data than Voyager's entire onboard memory. All of the navigation, all of the fault protection, all of the data formatting and transmission scheduling, everything the spacecraft does autonomously runs on 69 kilobytes. The constraint is not a limitation of the engineers who designed it. It is a statement about what precision engineering can accomplish within physical constraints. Every byte in that memory was allocated deliberately. Every subroutine was tested and retested. The mission planners could not afford errors, and they could not afford waste. The code written for Voyager was written by people who understood that there would be no opportunity for a service call. No technician could travel 24 billion kilometers to update the firmware. They had one chance to get it right. They got it right. The high-gain antenna, the large dish mounted at the top of the spacecraft, was engineered to maintain a precise pointing accuracy of approximately 0.1 degrees toward Earth. At Voyager 1's current distance, Earth occupies an angular diameter in the sky of approximately 0.00000034 degrees. To point the antenna at Earth requires knowing where Earth is, where the spacecraft is, and what the spacecraft's orientation is, simultaneously and continuously, to a precision that would not have been achievable by human operators acting in real time, even if radio signals traveled instantaneously. The pointing is done autonomously by the attitude control system, using the star tracker locked on Canopus and a continuous self-correction algorithm. The thrusters that adjust the spacecraft's orientation fire in bursts lasting milliseconds. A single thruster pulse uses an extremely small amount of hydrazine monopropellant. The spacecraft's hydrazine supply, used for attitude control throughout the mission, has been managed so carefully over 46 years that there is still enough remaining to maintain operations through the end of the spacecraft's active science mission. The engineers who calculated the propellant budget in the early 1970s were not certain the mission would last this long. They planned for a primary mission of approximately 5 years, covering the Jupiter and Saturn encounters. The hydrazine budget was calculated accordingly, with margins. The spacecraft has now been operating for more than 9 times the primary mission duration, and the propellant margins, carefully preserved through decades of meticulous operations, are still holding. Careful work, patient work, the kind of work that compounds across decades. There is something worth knowing about the team at JPL that operates Voyager 1 today. The spacecraft was designed and built by engineers, many of whom are no longer alive. The original mission controllers who managed the Jupiter and Saturn flybys are retired or deceased. The mission has been handed down across generations of engineers and scientists, like a very long, very careful relay race. The current Voyager mission team is small. A few dozen people maintain active contact with the spacecraft, monitor its health, plan its science operations, and manage the deep space network scheduling required to communicate with it. They work in an era when the technology surrounding them has changed beyond recognition since 1977. Smartphones, cloud computing, machine learning. While the technology they are operating remains exactly as it was designed 50 years ago. To communicate with Voyager 1, they write commands in a format that the Flight Data Subsystem's 1970s era processor can parse. They uplink those commands knowing they will not arrive for 22 hours, and that any response will take another 22 hours to return. A full command response cycle takes 2 days. In 2023, the Voyager team lost communication with the spacecraft for several months due to a software error that inadvertently caused the antenna to point slightly off Earth's direction. The team diagnosed the problem from the partial data that could be received, formulated a correction command, uplinked it across 24 billion kilometers, and waited 45 hours for the confirmation that it had worked. When the confirmation came back, when the signal returned to full strength, the engineers who had worked the problem for months were, by all accounts, relieved in the way that people are relieved when something extraordinarily difficult and important works out. The spacecraft recovered, the signal returned. The farthest thing we ever made came back to us across 24 billion kilometers of space, because a small team of engineers refused to give up on it. Let that sit quietly for a moment. Outside, whatever city or town you are in continues its nighttime rhythms. Traffic somewhere, wind in trees, the ordinary, half-noticed sounds that accompany the human night. None of it has anything to do with 24 billion kilometers of space, and yet the people who built the thing that is out there were ordinary people in ordinary buildings who went home at night and slept in beds not unlike this one. The work and the rest were always together. They always are. The interstellar medium that Voyager 1 is currently passing through has a specific name for the local region. Astronomers call it the local interstellar cloud, a region of warm, partially ionized gas that the solar system has been moving through for approximately 4,000 to 150,000 years, depending on the model used. The local interstellar cloud is itself embedded in a larger structure called the local bubble, a region of hot, low-density gas approximately 300 light-years across, thought to have been evacuated by one or more supernova explosions within the last few million years. The temperature of the local interstellar cloud plasma is approximately 6,000 to 10,000 Kelvin, as mentioned earlier. Its average density is approximately 0.3 hydrogen atoms per cubic centimeter, slightly higher than the surrounding hot gas of the local bubble, which has densities orders of magnitude lower. The boundary between the local interstellar cloud and the even lower density local bubble is a subject of active research, with models attempting to reconcile the measured plasma properties at the heliopause with the known properties of the interstellar medium at larger scales. Voyager 1 is helping to resolve these models. The plasma wave instrument's measurements of electron density in the interstellar medium have already confirmed that the local interstellar medium is denser and more structured than some earlier models predicted. Each year of new data refines the picture. The spacecraft is inside the object being studied. There is no other way to get this data. No telescope can observe the interior of the local interstellar cloud from outside it, because we are inside it. Only a spacecraft that has actually traveled there can measure it directly. Voyager 1 is the only instrument humanity has ever placed in interstellar space. It is irreplaceable, and it is still working. Let the breath deepen again. Your respiratory rhythm during slow-wave sleep is governed by the pre-Boettinger complex, but the oxygen saturation of your blood is maintained by a broader feedback system involving chemoreceptors in the carotid bodies, small structures at the bifurcation of the carotid arteries on each side of the neck and in the medulla oblongata. These chemoreceptors continuously measure the partial pressure of oxygen and carbon dioxide in the blood and adjust the depth and rate of breathing accordingly. When carbon dioxide levels in the blood rise slightly, the chemoreceptors signal the respiratory centers in the brainstem to increase breathing depth. When oxygen and carbon dioxide levels return to baseline, the drive decreases. The system operates continuously, adjusting breath by breath. Without conscious participation, your oxygen saturation right now, if measured with a pulse oximeter, is almost certainly between 95 and 100%. The hemoglobin in your red blood cells is carrying its full complement of oxygen. Your tissues are being supplied. Your brain, which accounts for only about 2% of body weight, but consumes approximately 20% of resting oxygen, is being served by a blood flow rate of approximately 700 to 800 milliliters per minute, maintained by the cerebral autoregulation system that keeps brain perfusion constant across a wide range of systemic blood pressures. Your brain is protecting itself, even now, maintaining its own blood supply with precision independent of sleep stage. Everything is running. You do not have to watch it. The golden record on Voyager 1 includes, among its sounds of Earth, a recording of a human heartbeat, 140 beats per minute. A resting heartbeat in a healthy adult ranges from 60 to 100 beats per minute, so the recorded heartbeat is slightly elevated, perhaps from a moment of mild exertion or emotional response. It was recorded as part of the brainwave recording of Anne Druin, who was serving as the creative director of the Golden Record Project. She was recorded while meditating, and afterward, she described having been thinking about the history of the world, about injustice and poverty and human suffering, and also about love. The recording of her heartbeat and brainwaves is encoded on the Golden Record. It is on the spacecraft. It is in interstellar space. The heartbeat of a human being who was thinking about love is now more than 24 billion kilometers from the sun, traveling through the local interstellar cloud on a trajectory that will not encounter another star for 40,000 years. There is no equivalent to this in all of human history. There are no cave paintings that traveled this far, no ancient texts, no artifacts from any prior civilization that exist beyond the atmosphere of the planet they came from. Every other human-made object that has ever existed is still here, on Earth, or in Earth orbit, or on the surface of the Moon or Mars. Voyager 1 is the only exception, and on it is a heartbeat. Let this be the last science before silence. In 1990, as Voyager 1 was approximately 6 billion kilometers from the Sun, having completed its primary mission and now heading outward, mission scientists proposed a final photographic mosaic. The spacecraft's cameras had been turned off to conserve power, but for a brief window, they could be reactivated. The team wanted to take a portrait of the solar system from outside it. On February 14, 1990, Voyager 1 turned its cameras back toward the Sun and took a series of 60 images, capturing 6 of the solar system's planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune, in a mosaic from 6 billion kilometers away. Earth appears in one of those images as a pale blue dot, smaller than a single pixel in the camera's field of view, suspended in a shaft of scattered sunlight that the imaging team described as a sunbeam artifact. Carl Sagan, who had advocated for taking the image, later wrote about it. He described the image as a demonstration of how small and fragile human existence is within the enormousness of space. He noted that every human being who had ever lived, every act of kindness and cruelty, every civilization, every religion, every king and commoner, was concentrated on that pale blue dot. That image exists because a spacecraft that had already completed its primary mission was asked to look back one final time from a position that no camera had ever occupied before, at the world that built it. The camera that took that photograph is now silent, but the image remains, and so does the spacecraft, traveling outward, carrying the record, carrying the heartbeat, carrying the diagram that tells a potential finder how to locate the world in the image, still going. Let the rhythm of these words slow now. Stage 3. Delta waves. Slow, synchronized, cleaning, growth hormone pulsing from the pituitary, glymphatic flow through the interstitial space of the brain, muscles released, eyes still, heart at its quietest rate of the day. Voyager 1 is moving through interstellar space. The signal is coming in. The 70-meter dish is listening. You are still. Both of these things are true at the same time, and both of them are enough. This is it. Thank you for listening about the Voyager 1. Quiet Science at Bedtime is still a very new channel. If tonight's journey gave you something, stillness or wonder, or simply the comfortable weight of closed eyes, we hope you will come back for the next one. A subscription, a like, and a notification turned on means this work continues. It means the next journey gets made. Thank you for traveling this far. And if you are already asleep, then you arrived exactly when you were supposed to. Sleep well. The signal is still coming in. 46 years, 24 billion kilometers, 22 watts, still. Good night.